Hello everyone, welcome to ICRA2020. Today we are going to present a topic called DeepCrashTest, which is a framework used for converting dashcam videos into virtual crash tests for automated driving systems. Before diving into the presentation, please be advised that there are some videos involving vehicle crashes that may be disturbing for some of the viewers and have been included only for informational purposes. Recently, we have witnessed a huge surge of research in the field of autonomous vehicles. Due to the safety critical nature of these systems, they have to be extensively trained or tested in an environment which deviates from nominal driving behavior. Currently, the methods used to collect the data for training or testing these vehicles mostly consist of normal or safe behavior. Extending these techniques to collect abnormal driving behaviors may be dangerous to the test drivers and also to the environment. To overcome this, researchers have been generating manual simulations for extracting adversarial data. However, those techniques may not replicate the real-world driving behavior. To tackle this problem, our goal is to extract valuable collision data in the form of vehicle trajectories from dashcam crash videos uploaded to the internet. The problem formulation for the whole setup is as follows. Given just a dashcam video captured using an unknown monocular camera, we extract the vehicle trajectories, including the ego vehicle's motion, and reproduce the trajectories in a vehicle simulator with a parameterization that enables further test case generation. By the end of the presentation, we will see how we can convert a real-world dashcam video into a simulated crash video. First, we'll be presenting a framework to extract absolute vehicle trajectories. Then we will discuss on the high level the steps to process these trajectories and recreate the scene in an existing vehicle simulator. And finally, we present the results and challenges of the framework. We follow strict assumptions for selecting the input video. All the videos are short and would not exceed 1 minute in duration. All the videos extracted are on the highways which have a straight or curved road without intersection scenarios. We assume the camera is always attached to the center of the dashboard. Also, we extract the trajectories only until the point of collision. This is the stage 1 of the framework, which is used to extract absolute vehicle trajectories. Having received the input video frames, we first pass them through a 2D vehicle tracking module which extracts the 2D tracklets of all the agent vehicles in the scene. We then use a 3D bounding box estimator to extract all the 3D bounding boxes for the agent vehicles in the scene. The sequence of the centers of these 3D bounding boxes form the relative agent vehicle trajectories with respect to the ego. We provide an alternate approach to estimate the 3D centers of the vehicles. To achieve this, we first use monocular depth extraction networks to extract depth of the scene and then use simple camera equations to generate 3D point cloud of the scene. We now utilize the outputs of the 2D vehicle tracking module to crop the region of the point cloud belonging to the vehicles. We can then apply simple averaging techniques to approximate the 3D centers of all the vehicles. The other part of the pipeline estimates the ego motion. We use an existing monocular visual odometry technique to extract a high-level ego motion behavior. We also use a combination of lane detector and tracker to extract low-level lane shift information. We combine this lane shift information with high-level visual odometry information to form the complete ego motion profile. Also, we can use the outputs of the lane tracking module to estimate the camera parameters using existing monocular camera calibration technique. These parameters can in turn be utilized by the 3D bounding box estimator or the point cloud estimation method. Most of the modules used in this framework are existing methods, but the selection of the methods and the design of the framework is novel and non-trivial. We will now discuss the individual components of this framework. The 2D vehicle tracking module comprises of an existing deep learning based object detector and tracker combined together with the help of a data association block. Within this data association block, we apply linear sum assignment to match the bounding boxes of the detector and the tracker at each frame to synchronize their outputs. The result of this block is a sequence of tracked frame with unique vehicle IDs. For the 3D bounding box estimation, we use an existing 3D deep box framework which takes in 2D bounding boxes and the original video frames as input and regresses the 3D bounding boxes with respect to the ego. We provide an alternate approach to approximate the 3D centers of the vehicles. This method can be used in case where there is accurate camera calibration. In this method, we first pass the individual RGB frames through a monocular depth extraction network to estimate the depth of the scene. We can then use standard camera equations to estimate or generate the 3D point cloud of the scene. At this point, we now utilize the outputs of the 2D tracking module to crop the region of the point cloud belonging to the vehicles. We apply simple averaging techniques to approximate the 3D centers of all the vehicles in the scene. For the lane detection, we use existing segmentation-based LaneNet method, and for the lane tracking, we apply linear sum assignment using Hausdorff distance between the lanes of the consecutive frames as a distance metric. To perform monocular visual odometry, we use existing optical flow-based method to extract high-level ego trajectory. We combine the low-level lane localization information with this high-level trajectory to provide full ego motion profile. Camera calibration is an important part of the framework. We use camera parameters for extracting 3D bounding boxes or for generating 3D point cloud. A proper camera calibration extracts accurate 3D centers of vehicles. We use an existing method based on accurate lane lines for camera calibration. However, due to the poor lane lines or the poor quality of the video, sometimes the quality of the camera calibration suffers. In such situations, we can use the parameters of the dataset on which the networks are initially trained. In the second stage of the framework, we combine the relative agent vehicle trajectories with the extracted ego motion to generate raw absolute vehicle trajectories. These raw trajectories are pretty noisy and need to be processed before sending them into a simulator. We use existing SimATAV framework to generate the simulations in a VBOTS simulator. The steps involved in trajectory processing are spline-based trajectory smoothing and noise removal, approximating the velocity profiles of the vehicles based on the frame rate of the original video. Since all the vehicles in the video start with non-zero velocities, to generate more realistic simulations, we extrapolate these trajectories to start with zero initial velocities. Finally, we provide an automatic classification scheme of agents based on their appearance or disappearance in the scene and vehicle heading. This kind of classification is very efficient for proper trajectory processing and proper simulation of vehicles. We now present video results. We provide 3 videos and their corresponding simulations generated by our framework. All the simulations use same smoothing parameters for the trajectories besides minor initial adjustments to the position of the vehicles as necessary. For this particular simulation, the spline smoothing has slightly altered the trajectory of the red car after colliding with the divider. However, we can always fine-tune or modify the spline smoothing parameters. We even provide a simple GUI tool with our software framework to make any minor modifications to the initial positions of vehicles if necessary. To demonstrate a typical use case of evaluating a collision avoidance systems using the simulations generated from our framework, we attach a simple emergency braking system to the ego vehicle for one of the simulations. An extension of this application is to randomly sample the initial conditions and parameterize the spline control points of the adversarial trajectories to extract safe trajectories. Some of the current challenges involved with the framework are videos are captured from different camera sources, which makes it necessary to do minor adjustments to the trajectories before sending them into the simulator. We expose software parameters to achieve this. Most of the videos have poor quality, which makes it difficult for the framework to extract proper features, and hence the accuracy is reduced. Monocular camera calibration from videos is still a pretty difficult problem. Also, the missing lane lines in most of the videos makes it difficult to do proper lane detection, and hence the accuracy of the ego motion is reduced. Also, the drifts in the ego motion estimation is a pretty common problem in monocular camera settings. Thank you for attending the presentation.